Hello everyone, welcome to this talk on dissipative anomaly in sliding droplets. I'm Vatsal Sanjay and I'm going to be talking about this work which was done by Gyandip Talukdar together under the supervision of Detlef Loze and myself, and we collaborate on this project with Christian Diddens and Udalok Sen. So before talking about dissipative anomaly in sliding droplets, let us ask the question, why do we even care about sliding droplets? Well, for that, I give you an example from nature where we have a plant leaf over here, where we see these droplets which are moving along. They are sitting on the superhydrophobic, let's say, leaf, and then they move along and then they coalesce and show very rich dynamics. In fact, if we look closely at these leaves, we would notice that they have these pillar type of structures which can entrap air bubbles between them that would then lead to such kind of behavior where the drop does not interact too much with the leaf surface over there. And we have been using this from nature, and we several of us have actually engineered these kind of surfaces in lab. So for example, if you take a surface and make these micropillars there and then put a droplet on top of that, you can actually approximate very closely what would happen for a hydrophobic surface in nature. As theoreticians, sometimes what we would fancy is that to even get rid of these pillars, because these pillars can sometimes pin the droplet, and it's not an ideal case to study these cases. And for example, an ideal, really ideal, no pinning, perfect superhydrophobic surface would be the one where we have a smooth surface which then has a thin film of air without these pillars, and then we have a droplet which sits on top of that. And of course, this is not stable because this thin film of air will simply drain out and the droplet would come in contact with the surface. And so this is just an idealized case, or if you may, the best case scenario that we could have when you have a droplet that does not touch the surface over here. So that would be basically a fantasy or a thought experiment for the theoreticians that you would think of these surfaces. What we could do as a first approximation is, instead of having air over there, what we could think about is to put lubricant, which is basically a viscous oil, on a surface, and then put droplets on top of that. And then we would also notice that these droplets would also slide along or slip on these surfaces. These surfaces are also colloquially known as a slippery surface, and as you can see, because of this oil layer which is kept over there. If we compare these two cases, neither of them have pinning effects, well, because there are no pillars, and if the both of them are smooth, then neither of them would give you any pinning effects. Neither of them have any contact with the surface, meaning the drop never touches the surface, either in this case or in this case. However, there is one key difference between the two, and that is on the case on the left, which is an ideal fantasy of a superhydrophobic surface. There is air, and basically there is 0 to very minimal viscous dissipation in this case. Whereas if we move towards this case where we have a lubricant, and as the drop moves on this lubricant, it will develop shear flow, and that shear flow would then result in viscous dissipation that cannot be neglected in the case that you see on the right. So the question that we asked today is that, is it possible to transform this lubricant infused surface that we saw into an ideal superhydrophobic surface? So is there any condition in which the case on the right would approximate the case on the left? So the viscous dissipation should disappear for that to happen. And for that, what we are going to do is that we are going to raise droplets down an incline, and we will simply study them both on the superhydrophobic surfaces and on the lubricant infused surfaces. What we are not going to talk about is the numerical framework that has made all of these simulations possible, all of these high fidelity simulations possible, and that we won't talk about today. Okay, so let's look at the droplets sliding down a non-wetting surface. So for that, what we have is basically a super amphiphobic surface over there on which we have a droplet sitting on it. Remember that there is an air layer between the drop and the surface that is ultra stable. Again, this is a hypothetical super amphiphobic surface. And we have the radius of the droplet, which is based on the volume of the droplet. the density rho d, the viscosity mu d, and the surface tension between drop and air given by gamma. And then, of course, we have air, where we have the density of the air rho a and the viscosity mu a. And of course, this is the whole setup, or this plate is kept at an incline angle of alpha over there. And as a result, the drop will move towards the left with some velocity u, which is the control, which is the output parameter for these cases. And the control parameters would be two, with three, in fact. So one of them would be the dimensionless viscosity of the droplet, which is given by the Ohnesorg number based on mu d, basically. Second is the bond number. You can think of bond number as the dimensionless weight of the droplet as we put them on the in the incline over here. And the last one is the angle, which is how steep is this inclined plate as we see over there. And of course, for air, we have the density ratio between the drop and the air, which we are going to keep constant at 1000. We won't change it. And second is the Ohnesorg number based on the viscosity of air, which also we are going to keep constant throughout the simulation. Now let us look at a typical case for bond number of 0.186, Ohnesorg of 3.45, and 13 degrees inclination. As you see, the drop very quickly after some initial transients over there reaches the terminal velocity, which is given by this plateau of the blue line over, as you can see, where the velocity ux is down the incline, and the velocity ui is perpendicular to the incline, which basically goes to 0. And these values are not out of thin air. In fact, we do this simulation because this is exactly the case that was studied by Richard and Quéré in one of the experiments, where they get a velocity in the dimensionless units of 0.1. Here, v gamma is the inertial capillary velocity scale. That is the same velocity scale we are also using in the simulations. And so both these cases give you a value of 0.1. And of course, as I mentioned, the drop does reach a terminal velocity. So as you can see from the plateau over there, and the drop configuration does not change. This you can also notice by looking at the green line over there, where this d is basically a function of the shape of this droplet, which also saturates to this constant value. Another aspect of this process is the hypothesis that this droplet is not sliding down an incline, but rather it is rolling down an incline. This is because if the droplet rolls as a basically a pearl-shaped droplet, then the minimum dissipation that you could have is when the droplet will be rolling down as if it was undergoing a rigid body rotation. And indeed, if we sit in the reference frame of the droplet, we do see the velocity field, which looks like that, which is basically a reminiscent of having a rigid body rotation down an incline, which is also the case for minimum dissipation in Stokes flow. In fact, you can ask the question, what is the velocity? And this was something which was asked and answered by Mahadevan and Pomo in 1999, where for the cases where the dimensionless weight of the droplet goes towards 0, then we have a pearl-shaped droplet, and that has a velocity scale which is inversely proportional to the dimensionless viscosity of the drop, given by 1 over 1 is org d over here, is directly proportional to the sine alpha. And then we have a 1 over square root bond number, which comes from the fact that we have a footprint of the droplet, which is in contact with the surface, which basically is a function of the bond number, and it gives you the scaling. Counterintuitively, in the limit of bond going to much larger than 1, these are the cases where the drop is quite heavy. So dimensionless weight of the droplet is much larger than 1. And there, the scaling is almost identical, except that the 1 over square root bond term basically drops out. And this you can also see because both in the driving and in the dissipation, both of them scale similarly with the same exponent in bond, and they cancel out from both sides. As a result, the bond number basically disappears. I urge you to look into this paper by Mahadevan and Pomo for more details of this process. And we can probe this scaling by normalizing on the y-axis the velocity normalized by the scale, except the bond number. Everything else, we have the Ohnesorg number, the sine alpha, and so on. And then we can plot this as a function of bond. And if these two scalings are correct, then we expect that in the limit of bond going to 0, we should have a scaling which is 1 over square root bond. Whereas in the limit of bond going to large values, here we should have a plateau which is independent of the bond number. And indeed, Here are the experimental results. These are the circles are the experimental results from this paper from 2001, and the triangles are the numerical results from our simulations. And what we see is that, first of all, that there's a good agreement between the experiments and the simulations over there. And whereas we also, and both of them are consistent with the scalings, both in the limit of zero bond and in the limit of bond going to much larger than one. And this is in fact consistent also if we go to a higher viscosity case. So now instead of 3.2, if we go to something which is 13.3, 13.6, and there also we see the same two regimes of scaling, and both of them basically give us the same result. Now, of course, what we could also do is to probe this sine alpha scaling. So because we noticed that in these two cases, both of them scale linearly with sine alpha, and we would like to now probe the scaling with sine alpha. Of course, here we have a u star, which is the velocity for that particular system that we would get if this alpha goes towards zero. So in the limit of zero alpha, then we get the scaling. Now, of course, if both of these scalings are correct, then we expect basically a sine alpha independent plot over here, because remember that we have compensated the y-axis with sine alpha, and so for those two scalings to be true, we should basically expect a horizontal line, which is what we are getting over there, which is consistent with this picture of having a proportional velocity proportional to sine alpha. Now, surprisingly, what happened is if we go beyond a certain value, in this case, this is sine alpha value of 0.5 roughly, to 0.5 or 0.6 roughly. And what we notice here is a systematic deviation away from this plateau. And we can see it over here. And this, of course, is because the theory from Mahadevan and Pomo is only valid in the limit of small angles. And of course, if we have a finite angle, then something changes. What is remarkable here is that this change is systematic and also seems to follow some sort of scaling. And this is what we would like to understand. So we would like to understand why do we see this deviation away from the plateau or the scaling at small angles, which worked quite well over there, but now deviates away quite drastically as we go to large enough values of sine alpha. For that, let us look at one case. So we are going to look at this case over here. And now here I'm co-moving with the droplet. So, and the colors here in the darker the color is, the higher is the velocity or the speed magnitude, and this drop is moving towards the right. And you can notice once again is after the initial transients, the drop takes a constant velocity, consistent with the picture also below, which is basically this plateau over there. And the shape also goes to a constant value. So the shape is also invariant in time once we have gone past the initial transients. What is interesting is that if we look at the shape over there, the nose and the tip and the tail of the droplet have different curvatures. So you have a kappa 2 and kappa 1. So if you think about the pressure just inside these, the nose and the tail, then we have different pressures. And of course, this is a moving droplet, and that's why it can sustain these two different pressures. But what is going to happen is that these two difference in pressures at the tip and the tail is going to create a resistive force, which is analogous to this paper over here by these authors, where they show that the pressure difference in the nose and the tail can provide a resistive force to a moving, let's say, drop or a trapped liquid. And this force, in fact, scales in such a way that if we write down the scaling for the velocity, that would be sine alpha to the power 3/2. So I urge you to look into this paper, and you would get this velocity scale of sine alpha to the power 3/2, which in fact is consistent with what we have here. So this line here is square root, and that's because we have already compensated with sine alpha. So if you take the sine alpha to the right hand side, then basically this scaling here would be sine alpha to the power 3/2. Now, of course, if we go even to sine alpha close to 1, which is alpha close to 90 degrees, there is a systematic deviation away even from this scaling over there. And that's because when you are exactly vertical, so for this case over here, we have vertical plate and a droplet sliding down. We notice that in most of our cases, the drop would simply peel off from the surface and would just go away, as you can see over there. And so, of course, we don't expect this scaling to hold once we approach 90 degrees inclination angles. So with this picture, so we let us move now towards droplets sliding on lubricant infused surfaces. And for that, we now have way more control parameters. In fact, we will still have the dimensionless viscosity of the droplet given by Onazog D, so OHD. And we will have a dimensionless viscosity of the film, which we can donate with OHF, so Onazog number for film, so F for film. For these cases, we're going to keep the bond number same as 1 because we understand quite nicely how these things change with bond. And so we are simply going to go ahead and fix the bond number to 1 and look at the other control parameters. For these cases, we have assumed that the density of the drop and the film, the ratio is 1. Of course, there would be slight differences in the density ratios, which won't be unity in real life cases, but it is roughly very close to 1 in fact. And of course, we keep the density of the surrounding as compared to the liquid at 0.001, which again is the same as the water-air density ratio. And we keep the Onazog number based on the air viscosity also constant at 10 to the power minus 4. With that, this is a typical case. This is for alpha equals 30 degrees. And once again, we notice that as we start moving the droplet, it slides down, and then it actually comes to a steady state, and then moves down with a constant velocity. At this point, it also has a finite thickness of oil on which is covering this droplet. I must have mentioned that, in fact, that in our simulations, we assume that the drop is always cloaked by the lubricant layer. So even at T equals to 0, there's a thin lubricant layer, which of course, because of dynamics, would come to a steady state, as you can see over there. But even in the beginning, we assume that there is a lubricant layer on top of the droplet. All right, so now what happens if we compare these cases against the experiments? So now these are the results from the simulations, and these circles are from the experiments. Now the comparison is not as exact as we have seen for the superhydrophobic cases, and our working hypothesis there is that it's because of the two-dimensional versus three-dimensional effect. So all the experiments, in fact, are 3D. So these are droplets sliding down an incline, whereas to keep the computational cost at bay, what we have done here is that we have only solved cases where we assume these droplets to be cylindrical. So these are 2D droplets sliding down an incline. What is still remarkable is that the scalings and to both of these asymptotes, so the constant that you see over there and this 1 over Onazog that I will explain in a minute, both these scalings are agnostic to whether it is a 2D system or a 3D system. What changes is the exact value or the prefactor that goes in front of these scaling analysis. So in fact, what we can do is that in the Onazog film versus Onazog droplet parameter space, we can vary the Onazog number of the droplet at 3 discrete values of the Onazog film. And once again, we would notice that we get these two regimes. So one is the 1 over Onazog D regime for the viscous regime, and a constant, so where U goes as the inertial capillary velocity, which is again these plateaus that you see over there. Now, the black data points here and the line that we see there, that is for, if a droplet slides down a superhydrophobic surface, as we have shown in the previous part of this talk. Another interesting thing here, just to note here, and then I would come back to this later on, is that the difference between 0.5 and 0.005 is larger as compared to the difference between these two over here. And in fact, which means that the cases here are saturating towards a constant value, whereas the difference between the brown cases and the superhydrophobic cases are quite a lot. And we'll again come back to this in the last part of this talk. Okay, so for now, first we asked Can we explain this 1 over Onizog D dependence? This is a dependence that we have seen in the previous slides. And for that, I show you two pictures. That on the top, we have the velocity field, and on the bottom, we have the log 10 of the viscous dissipation function. It's done on a log 10 scale so that you can identify the differences between regions of high dissipation in dark color and the regions of low dissipation, which are in light colors. And as you can see here, is that most of the dissipation happens in the droplet, and in fact it still is kind of very close to the footprint of the droplet, as you notice over there. And this is, again, recall that this is the same argument that was made by Mahadevan and Pomu when they were looking at droplets sliding down a superhydrophobic surface, where in the limit of small bond numbers we basically have high dissipation close to the footprint and in the droplet as compared to the surrounding. And that would give us this correlation which is basically 1 over Onizog droplet, which is consistent with the highly viscous regime, as you have seen over there. Now we can play the same game, but instead of varying the Onizog droplet systematically, we can vary the Onizog number of the film systematically at two discrete values of Onizog D. One is 0.1 and the other is 1. And once again, if we see this, so we get two distinct regimes once more. One in the limit of Onizog film going towards 0, we get a constant value, whereas in the limit of Onizog film, which is larger, well, approaches 1, and then we get this 1 over Onizog film dependence. In the same way, we once again ask, can we explain the 1 over Onizog film dependence? So the same plot here, the only difference is that in this case now, the Onizog film is higher than the Onizog droplet. It's on the same color scale as before. And you can see that the dissipation is now much more concentrated in the film, particularly in the close to the tip of the droplet and close to the tail of the droplet, where basically the regions are completely dark black, which denotes regions of very high dissipation. This is once again the same thing shown over here in a better way, and we indeed see that the regions of close to the nose and the tail of the droplet inside the film has very high dissipation. And here we draw an analogy between this motion of drops and bubbles inside wedges, where we have a similar, let's say, system, and in those cases the force that is acted because of the presence of these high regions of high dissipation is basically given by this expression over here, which if we incorporate in our for our case would give us a 1 over Onizog film dependence, along with some dependence on this bond and the sign alpha and so on. But the main part is this leading order dependence on 1 over Onizog film. And this is what would explain this 1 over Onizog film dependence for this case. But in all these cases, I have been hinting about the cases, what happens when our Onizog film goes towards 0, and that's really the main point of this work. In fact, if I show you in these cases, there is another limit where in the limit of Onizog film going towards 0, we do get a constant velocity independent of the Onizog number of the film. However, this velocity is actually still quite far away as compared to the velocity of the droplet as they fall down the incline for a superhydrophobic cases for exactly the same conditions. So the green line and the red line over there, they have identical droplets. The only difference is that in for the symbols here we have a Onizog film because we have a droplet sliding down an incline kept on a lubricant infused surface, whereas for these cases we have a ideal superhydrophobic surface, which is really the upper limit for these cases. And what we notice here is that the velocity for the limiting case of Onizog film going to 0, which also almost reaches a plateau, as you can see over there, is not equal to the case where we have Onizog film 0, which is basically air, which is these lines over here, as we can see. So why is this? So why is there the velocity in the limit of Onizog going to 0 is not the same as velocity for Onizog number exactly equal to 0? And here is one such case where you notice that there is some dissipation in the droplet, which would also be the case if we think about superhydrophobic surfaces, where again the dissipation is primarily in the droplet, which is still consistent. What is different is that these boundary layers that you can see over here and over there, so close to the uh, to the to the tip and the tail of the droplet, and these boundary layers are there because we have a viscous system, we have a viscous film where these do exist, and in fact they contain viscous dissipation in these thin boundary layers. And even if we start systematically making the Ohnesorg number of the film go towards zero, these regions don't really disappear. They are still there. They become small, but they still exist. And if you integrate the viscous dissipation close to the plate, they in fact still give you the dissipation. So if we look at like where is the dissipation, so for the superhydrophobic cases, it's all in the droplet and essentially negligible in the air. So there's no dissipation in the air. Whereas because of the presence of these this film and this boundary layers over here, we have a case where basically there is a non-zero finite dissipation in the film, even in the limit when the Ohnesorg number goes towards zero. Now, this is also the difference between having an Euler equation or having a Navier-Stokes equations, because when you have an Euler equation, which is true for the cases where viscosity is identical to zero, then of course you don't have these boundary layers, and there we won't expect to have any viscous dissipation. Whereas the moment we have some dissipation, in this case for the case of viscous oil, even if this viscosity is quite small, we still have dissipation. Now, of course, I must remark here that these very extremely small Ohnesorg numbers of the film might not be experimentally viable, because in order to have such lubricant infused surfaces with small Ohnesorg numbers might not be so easy to get. Well, so just to come back to the question that we asked in the beginning, that is it possible to transform a lubricant infused surface into an ideal superhydrophobic surface? The answer to that is no. And that's because the velocities that we get in the limiting case when this Ohnesorg number goes towards zero is not the same as that of superhydrophobic surfaces, where which has the least dissipation, and whatever we do, as long as there is finite dissipation in the film, there would always be boundary layers, and they would always lead to dissipation, and this dissipation would basically not disappear. This is something that we can think about in terms of dissipative anomaly, where the limiting case of viscosity going towards zero is not the same as viscosity being identical to zero. So are there other systems where this dissipative anomaly is apparent? And yes, it is. So for example, if we think about bursting seeds, so we imagine that we have a liquid sheet which is infinite, and we poke a hole at the center, and we let this hole open up. So now this is a infinite sheet with hole that you see over there. And this is the axisymmetry. On this side, we have velocity field normalized by the so-called Taylor-Kulik velocity. So for this system, we know that the velocity of the tip goes towards this constant value, which is the Taylor-Kulik velocity, which you can get either using a momentum balance or by doing an energy balance, where you have to account for the dissipation that happens inside the blob. So once again, this is log 10 of the viscous dissipation function, where you notice that we have these regions which are black, which are quite extreme, and the closer we go to zero, so here the Ohnesorg number of the film in this case is 0.05. The closer we go towards zero, this neck becomes quite thin, but it never disappears, and as a result, we always get this extremely high gradient that leads to extremely high, or that leads to a finite dissipation, and this which finite dissipation does not go to zero, and this again is a same case of having this anomalous viscous dissipation. In fact, this is one such case where we can calculate the viscous dissipation exactly. So for that, I take you to this introductory lecture by Pierre Dejean, where essentially what we have to think about is that if we sit in the reference frame of the rim, as this rim as this hole opens up and this rim grows, if we sit in the reference frame of this tip of the rim over there, then what we will see is that we have a mass m of the film, and all the fluid parcels coming in from the sheet, which are dm, they're moving with a velocity v, which is constant in time, and then they hit the rim, and then they come to rest. And essentially what is happening here is that we are losing the kinetic energy from these fluid parcels coming in from the film and hitting the blob over there. And as a result, we get a viscous dissipation rate, which is half dm dt v square, which coincidentally is identical to the rate of increase of kinetic energy in the system. So in fact, we see here in the simulations that the rate of increase of kinetic energy is almost identical to the rate of viscous dissipation in the system, which are both given by this expression half dm dt v square. And as a result, in this problem of classical Taylor-Electric fractions, the tip goes to a constant velocity, which is given by this expression over there. And this is once again a singular limit. So the limiting case of Onizog going to 0 is not the same as Onizog number equals to 0, because of course for Onizog number equals to 0, the dissipation would disappear, and we would simply have no dissipation in the system. But in this case, as long as we have a finite viscosity, the dissipation is always independent of the viscosity of the system. And there are in fact other systems. So this was a retracting sheets system. There is another. Recently, there have been some papers about retracting sheets and escaping pinch-off, where the authors have shown that indeed this limiting case of Onizog going to 0 and the Onizog equals to 0 give you quite very different results, and that's because of this presence of these high viscous stresses close to the neck over there. Similar features are also apparent in cases like drop impact, where an impacting drop would never be able to recover all its energy, and that's because most of the energy is lost at the moment of impact when there is a viscous boundary layer which is diffused inside the droplet over there. Lastly, also for freely concentric free surface waves, once again we saw that if we have waves that focus at the center, then also we have some behavior which is very similar to having these viscous anomalous behavior, where dissipation does not go to 0 when we go to small enough viscosities. So with that, I would summarize this the viscous dissipation or viscous anomaly discussion for in the case of let's say sliding droplets, where we found a new scaling for the drops on high incline. We also saw two asymptotic regimes for the variation of Onizog droplet as well as for the variation of Onizog film, where in the limit of small Onizog numbers we have a constant velocity, whereas in the limit of high enough Onizog numbers we get a scaling which is one over Onizog number. And then of course we have this dissipative anomaly, where the limiting case of Onizog going to 0 is not identical to Onizog number equal to 0, because there is a difference, and that's just because of these boundary layers that are created where the dissipation never really disappears in the limiting case when Onizog number is small but finite. So with that, I would like to thank you for your attention and would love to take any questions.